Preconditioning Matrix-Free Operators, is that right?
Yes, I ingested part of Valeria's poster.
All right, sounds good.
So, this is a little bit more of an overview, which works fine because preconditioning is hard and I didn't get as far as I wanted. We're yet another group under the Exascale project, specifically the SEED project. Sort of big picture, we're trying to be an extensible library for high-order finite elements with a matrix-free implementation and easily flexible user code. So I'll show some pretty nice results we've seen on that front. Talk a little bit about optimizations we've had, and just sort of a little bit of what's going on with us in terms of what we're working on. Getting ready for the Exascale is the purpose of the SEED grant. It's kind of what all of us are doing right now as these machines are coming online in the next few years. So we're starting here with the assumption that we want to be working on meshes that are predominantly full of tensor product elements. You can get meshes that are mostly nice tensor product elements, and if you can do that, then you get nice performance benefits because it is cheaper to apply basis operations in terms of flops and also just memory storage required. So we are completely trying to avoid matrix assembly so that we can get access to these tensor product optimizations. And just because that's not ambitious enough, we're also trying to provide nice optimized implementations of these tensor contraction optimizations for both CPU and GPU so that you don't have to write your code twice. And we're trying to set it so that you have a single source file for your physics that we go ahead and ingest and mangle appropriately for the GPU. And we don't even care if you hand us a mix of CPU and GPU nodes because we're completely a non-node library. So sort of big picture what we try to do, whatever you're using, your code base, currently we have examples with MFIM, NEC, PETSI, but this is a C API. We also have a Fortran 77 API if you really love that Fortran. Calls through to libCEED, and then libCEED has multiple backend implementations that go ahead and provide that those highly efficient tensor contractions. So really to highlight on the CPU side, we're getting our best performance from libXSMM, which is a nice library put together by Intel doing small, dense matrix multiplies. And on the CPU side, we're actually doing some nice code generation, which is giving us performance which is plus or minus 10% of handwritten code tuned for specific machines, which is lovely. How do we do this? We start with basically starting with the same sort of operator decomposition you'd see from finite element theory. All of these pieces are things that you would need to assemble a sparse matrix. We, the library, just want all of these individual pieces that are already laying in your code so we can rearrange things and do this in a matrix-free form that makes good sense for whatever architecture you're running on. So we have the parallel communication piece. That's above our heads. We are strictly on node. So you are responsible for the parallel communication, the parallel gather-scatter. But on node is where we start. We have a local gather-scatter operation, which is just a way to break down into individual elements on your mesh, the mapping from those nodes to an individual element. Then we have basis operations. You provide the matrices. We have a couple of convenience constructors, but we're not actually attached to any specific discretization. This is completely an algebraic sort of representation right here. So as long as you have a matrix that represents interpolating from your nodes to your quadrature points and taking derivatives from your nodes to your quadrature points, that's what we need. So that's our basis operations right there. And then we have D, which is the exciting part, which is the physics, which is a block diagonal function representing your physics at every single quadrature point. However many fields you have, it's Navier-Stokes, it's a 5 by 5 block. And then coming back, we have our basis transpose operations. You can think of that as test functions, applying the action of your test functions. And then we have that transpose of the local gather scatter. That's assembling all of the actions of the element operators into a local operator. So that's what libCEED handles, is this local operator. Just a quick example, how to set this up in Laplacian. This works like nicely, but it's just a little bit of conversion from standard notation to our notation, because like we're using B's and D's and all sorts of ways different than normal theory. So this is the generic form of libCEED operator, and then right here we have a Laplacian. So looking at that weak form, we're taking the derivatives of our inputs. If we're in 2D, we're going to be taking a 2D gradient, 3D gradient, and then we've got some sort of, in the middle here, sort of geometric factors we've got to account for mesh deformation, and we also go ahead and just pack in our integration weights at the same time. And then we, if we're doing a symmetric form, then we actually have the same B on each side, and this B right here is, like I said, our action of our test functions, and then we've got our gather scatter on either end. So in our case, if we have a static mesh, a lot of times what we'll do is we'll just pre-compute all of our geometric factors, take the mesh coordinates, go ahead and apply derivatives, build up a Jacobian for the geometric factors, and wrap all that in a pre-computed. But we could definitely also just add coordinates as a separate field if you have a moving mesh that's changing all the time. Doesn't particularly change what we do. And once we have this, we can start on our back-end side working in optimizations. So if for our tensor product dominant elements, no surprise, we start putting in tensor products to tensor contractions to do the derivatives for us. And in 3D, we actually have this nice little benefit, which looks horrible in 2D, which is we actually interpolate first to our quadrature points, 3 tensor contractions, or 2 in the 2D case, and then we apply derivatives, another 3 tensor contractions, or 2 in 2D. Same cost in 2D, cheaper in 3D, but we have the side benefit of if we're dealing with something like, say, your Navier-Stokes equations, where you want both interpolated values and derivatives at the quadrature points, this sort of two-stage setup gives us both for 3 tensor contractions instead of 12, or 6 tensor contractions instead of 12. So we're cutting our flops down in these basis sections. Actually getting the two-stage bit is a little bit of an optimization that's a work in progress, but we've got all the pieces we need there for it. On the code side, this exactly follows the beautiful sort of finite element theory that you'd expect it to. We just ask for all of these separate objects that are required for every single field. I've got a input field, derivatives of u, and then I've got my basis objects, I've got a vector I'm acting on, I've got my gather scatter object. It's like all bundled together quite nicely. On the QFunction side, same thing. We're asking for all the inputs and outputs independently. So this is a kind of a snapshot looking at our C API. This is sort of like readable just as like straight sort of math almost. These are all of the components of my PDE. This is the type of basis I'm using, H1 Lagrange, whatever, all sitting right here. Here's the exciting part for us. We just last month started being able to use one source file for both the CPU side and the GPU side. And a lot of this is thanks to work from Johan, one of our collaborators over at Livermore. So you, the user, write a single C++ looking file, header file, And in there, you just write a loop that says, here's what we're doing at every single quadrant point. So this is the 2D Laplacian. I've got my geometric factors. I've got my derivatives. My outputs are what will get multiplied against the test functions derivatives. This ends up getting compiled with your main program for the CPU side. For the GPU side, we go right into the header, grab that source, drop it into an appropriate kernel, compile that kernel, and run. And the exciting thing is we're getting really nice performance. So we have a set of benchmark problems attached to the library. It's a basic apply the mass matrix, apply the Laplacian. Laplacians are everywhere. It seems like a fair benchmark problem, just to give you a feel for how we do in your particular environment. I want to look at specifically showing you some results from our benchmark problem 3, the scalar Poisson problem. This is what we get from going to the beautiful single source. You write C and we turn it into an appropriate device function for you. This is what we had before, where the user would provide the information for the element gather scatters, the basis operations, and the device kernels for the QFunction, and we would apply each of those separately. And we just moved to code generation, where we take that user QFunction, drop it in the middle of a device kernel, put the gather scatters and the tensor contractions on either side of it, and run that as a single kernel. And this is the sort of performance boost we're seeing. So here on the y-axis, you're seeing a sort of a measure of throughput, sort of efficiency sort of thing going on here. That's degrees of freedom per second times CG iterations divided by the number of MPI tests we've got times seconds. So sort of a measure of throughput. And problem size on the bottom. And I mean, this isn't horrible performance, but the jump when we did this code generation is quite lovely. And the thing that's really exciting is the person who was doing all this code generation for us, Johan, he spent a week with Tim Warburton's group out of Virginia Tech, added a lot of nice improvements to his code, and now our code generation backend for CUDA gets plus or minus 10%, sometimes plus, sometimes minus, 10% of the libParaNumal kernels that his team out there at Virginia Tech wrote specifically for specific computers, specific GPUs. So I think this is a win. You get to write C, and then we turn it into a single device kernel that gives comparable performance to something that was tuned specifically for a given device. You win, we win, everybody's happy. On the GPU side, we're getting nice performance, and then we take that over to the CPU side. Like I said, libXSMM is currently giving us our best performance. They've been great, super responsive to, hey, can you add this to your library for us? How do we do this in your library? So if you ever need libXSMM for some reason, super responsive dev team. They're great. This is Haswell nodes, so not super impressive. We actually get up to something like another 100,000-fold, I think, if I remember right, on the Skylakes. Skylakes just, they're better chips. The thing that I wanted to highlight here is on the CPU side, we have the opportunity to play with vectorization strategies. So we can either vectorize across elements. So for low order elements, each element is pretty small. We can put together a whole bunch of elements, and it fits nicely into cache. With multiple elements, we interlace 8 elements, and we know that we're a multiple of vector length. everything's happy for vectorization. And at low order, over here, you can see we're getting higher efficiency, higher throughput from our low order problem size on our low order basis elements on our benchmarks. Whereas over here, you start getting the individual elements big enough, and we're starting to creep into that spectral element range, then our elements are heavy enough that one element has enough opportunity for internal vectorization that we can actually get really nice performance processing one element at a time rather than interlaced batches. So there's a little bit of like interesting performance trade-off there that we need to learn how to communicate to the user. We've got options for both, whether or not the user wants to try to explore internal or external vectorization based on what sort of a regime they're running in. Super high order, something in the middle.
What's the difference between the left and right?
This is running one element at a time. This is running batches of 8 elements at a time for our tensor contractions. So when we're getting up to, what is it, like 9th order or so, we start to see that it gets too big to fit into cache nicely, and we see that drop off in performance. And that's when you would want to switch over to single element processing across your mesh. On our to-do list is sort of we benchmark your code and then provide a recommendation for which mode you want to run in. We do have more than just toy examples sitting out there in our library. We aren't just a library for applying mass matrices and Laplacians. That would be very dull. With that user-defined QFunction, we wanted to sort of put some examples out there demonstrating that you can really put some heavy physics into these user-defined functions. So we have a Navier-Stokes example. This is doing actually a atmospheric, in its standard configuration, atmospheric demonstration where you take a pocket of cold air and let it fall, hit the ground. Boundary conditions are a little fiddly right now, so it's not as clean as we'd like, but it's actually nicely processing everything just fine. And it's using 3D compressible Navier-Stokes just fine, so that's handling 5 fields of input, and that's actually a pretty flop-heavy quadrature point function, and we're actually getting nice performance out of that. We actually have in there, we're putting in a little bit of a pragma at the top of our quadrature point function loops that says, hey, compiler, you should try to vectorize this. And we're actually getting vector instructions out quite nicely from users are just putting in code in the top of their loop. We put a pragma to do SIMD, and we're actually getting FMAs out of the compiler, which is quite nice. Granted, the user can still write terrible code. There's only so much we can do, but we can actually kind of help the compiler along to take whatever you want to cook up and make it something that works quite nicely with our optimized tensor contractions for our basis evaluations. We're currently in the process of expanding our example suite, especially on the fluid side. I don't know if any of you are familiar with Ken Jensen over at CU. He runs Pasta. It's a fluid solver. But collaborating with him, some of us on Jed's team, him and some of the folks on his team, we're looking at doing an example with SUPG stabilization, doing a primitive variable formulation rather than a conservative variable formulation. Switching over, right now we've got an explicit time stepper, just switching over to an implicit one. So we need some Jacobians of our quadrature point functions. Just kind of like demonstrating just how far we can take this basic framework that we've got with our library. And we're also starting the initial development of a shadow water equations example. So right now we're working on a Poisson demo on the cubed sphere. And that's sort of our halfway point to a shallow water equations example. On my side, the part that I was going to talk about, but I'm kind of slow, we're working on preconditioners. So we actually know, so kind of one of the pitfalls of matrix-free, right, is that matrix-free locks you into iterative solvers. And if you're doing iterative solvers, especially with high-order finite element operators, you've got to do some preconditioning in order to get your condition number down so you can converge today. So we're looking at, given our operator decomposition that we actually have a lot of information. Sure, that quadrature point function is very flexible, very general, but we know a lot of information about our PDE that's being specified. So we're trying to provide options to the users from the decomposition that they provide. There's a lot of linear algebra sitting right there. Can we provide some building blocks that can become good preconditioners? So I just need another couple of days to sit down and knock out an efficient diagonal computation. So that's sort of a nice first step if you've got diagonally dominant sort of an operator you're looking at. That'll work just fine. But we have an example that's in the works, getting a little bit of refinement. It runs, but I want to make it run nicer with the CUDA side, where we're doing P multigrid. Works nicely for elliptic operators. And we can actually handle, we did P multigrid because we loved matrix-free. We can go ahead and jump right into unstructured meshes quite naturally. And then P multigrid is much more natural than H multigrid on unstructured mesh. And we, libCEED, actually know nothing about your mesh. We just know how to get to individual elements. So P multigrid is a nice fit, and we can actually do all of coarsening or prolongation for you, which is kind of nice. Well, you'd have to set up how to get from a high order to a low order basis, but you can build a libCEED operator that does that matrix-free, which is nice. We're also working on an interesting sort of thing that I'm excited about, but like I said, didn't do enough to be able to talk about it yet, doing a BDDC for high order finite elements, where we're using a fast diagonalization method to do those subdomain solves on each element. And for something that's separable, that's an exact inverse using fast diagonalization. Everything works great. The question is, for me, what sort of things that aren't separable are close enough that I can use something that looks like an element inverse that came from fast diagonalization? If I can know how the eigenvalues of those element matrices are going to change in some predictable way. The matrix deformation was nice enough that it isn't separable, but I can get close to knowing how the eigenvalues are going to behave. I might be able to get an inexact solver, and there's been lots of work doing BDDC with inexact solvers on the subdomains. So I'm trying to link into that work. So we've got options on the preconditioning front. That's sort of a work in progress that is always a work in progress because preconditioning is hard. So there we go. That's what we're working on right now. Performance enhancements always. We can do mixed meshes. We can do unstructured grids. We can do operator composition. We just want to do it better. We want to expand our examples. We want to give you more preconditioning options, algebraic differentiation of the user functions, so we can build Jacobians for you. And really, we're at the stage where we need contributors and friendly users. Well, contributors we've got pretty well covered, but you're welcome to become a contributor. GitHub gets lonely sometimes. But we need friendly users. We're learning a lot from these examples as we have collaborators of what is needed in our library. There we go.